Hello and welcome to this session. This work is part of MFMET for establishing metrology standards in microfluidic devices, a European project financed by Ampere. I am Kevin Romieux from CETIAT, and I am going to talk about wettability measurements for microfluidic devices. In the second part of this presentation, my colleague from LNE will present roughness measurements. Let's first define the interest of wettability. It helps explain the liquid behavior when it is in contact with a solid surface. Large quantities of liquids are mainly influenced by gravity, but the interaction forces are not negligible anymore for small-scale volumes. For instance, the shape of a drop of liquid is very different depending on the wettability of a surface. It will be very flat for a hydrophilic surface and almost spherical for a hydrophobic one. In a closed capillary, wettability will also affect the shape of the meniscus at the interface between air and liquid, which may affect optical flow measurement techniques based on front tracking. In general, wettability has an influence on the resistance to flow and the pressure drop. Wettability can be characterized by the contact angle between the surface and the line tangent to the drop at the contact point. It depends on the material and the fluid. However, by measuring several contact angles with different liquids, it is possible to evaluate the intrinsic property of the solid material, which is its surface energy. This method is described in an ISO standard 19403. Let's see how to evaluate the surface energy of one solid material in practice. The surface energy is the sum of a dispersive component and a polar component. The idea is then to find a relation with these two components. This has been done by Owens, Wendt, Rabel, and Kelbel, who designed a linear model between two quantities, x and y. X only depends on the liquid properties. This can be found in the scientific literature. Here are some examples. For each reference liquid, we know the dispersive and polar fractions, and the sum of the two is the surface tension of the liquid. Then, y is related to the measurements of the contact angle with several reference liquids on the same solid surface. The properties of the liquids also appear in the expression of y, but we already know them from the previous table. We can now plot y as a function of x and estimate the linear trend of this dataset. The y-intercept is a constant directly related to the dispersive component of the material. On the other hand, the slope is related to the polar component. We now have everything to estimate the surface energy of our solid surface, and the model can be fully written under this form. I will now show you some results obtained for the MFMET project with the test setup in the metrology laboratory at CETIAT. You can see here the camera, here the backlight, and in between the slide with the liquid. This slide is made of borosilicate glass, which is frequently used for microfluidic devices. This is the kind of image you obtain with the setup. After image analysis, you are able to measure the contact angle and repeat the process with several reference liquids. You also repeat the process several times for each liquid in order to evaluate the intensity associated to the measurement. Now you can plot the data using the model I presented before. We know the y-intercept is the square root of the dispersive component, and the slope is the square root of the polar component. Thus, we calculate the surface energy of this material with the associated uncertainty. One quick word about traceability. Like any metrology project, the measurements must be traceable to the international system of units so that different laboratories following the same process are able to compare their results. Here, it is the angle measurement method that needs calibration. This is done by using a standard printed on a transparent slide. After taking the picture with the camera of the setup, we apply the same process on the image to measure the angle and compare it to the reference value. That's it for wettability. If you want to know more about it, I invite you to read this report written by the team of the MFMET project, available on our website. But wettability or surface energy is not the only characteristic of a solid surface that can influence the interaction with the liquid. I am now pleased to hand it over to my colleague from LNE for the second part of this presentation about roughness.
Thank you, Kevin. My name is Alexandra Del Valle from LNE, the French Metrology Institute. As mentioned by Kevin, I will focus on the roughness measurement of microfluidic devices by atomic force microscopy. Atomic force microscopy, or AFM, is intensively used in the laboratories involved in measurement at the nanoscale level, especially for topographic measurements, and in our case, roughness. Basically, the principle is to scan a mechanical probe constituted of a cantilever and a tip, which have a typical apex of few nanometers, and over a surface. This system probes actually the interaction forces between the tip and the surface. The movement of this probe could be censored through a laser photojet system. In fact, a laser is reflected on the cantilever, and the photojet measures this displacement. Moreover, a feedback system ensures the tip to be at the same distance of the sample on each point of the surface. A 3D image could be constructed by gathering each point of coordinates x, y, z. The reconstructed topographic image consists in a cloud of points. Moreover, measurement performed by AFM is easily traceable to the Système International d'Unité, or SI unit system, in other words here, the meta. The pyramidal figure here represents the traceability route of nanoscale measurement implementing a metrological AFM. This reference instrument makes it possible to link the nanoscale dimensional measurement to the SI unit through a calibration process implementing transfer standards, that is to say, step heights or periodic ratings. At LNE, routine nanoscale measurements like nanoparticle sizing or roughness measurement are realized with commercial instruments calibrated with grating standards as represented here. The grating standard have been previously itself measured by metrological AFM, which ensure it to be a reference. In fact, the metrological AFM implements interferometer measurement to control the tip position in relation to the surface. These measurements are linked to the top of the pyramid, the SI meter, through a continuous sequence of calibration. The traceability of high nanoscale measurements are well managed thanks to the availability of a wide range of transfer standards. That is not the case for roughness traceability. Transfer standards for roughness does not exist. However, all the standardization for roughness calculation is well established. In fact, these calculations are similar to those developed for profilometers, for example. At the right of the slide, you'll find an example of calculation of SAE parameter, which is well defined in the ISO standard 25178-2 and correspond to the arithmetical mean of the absolute values. In the frame of the MFMET project, we measure the SAE parameter for 3 images at each different location of a glass microfluidic device. Images were acquired in tapping mode, scan size is 555 micrometers squared, and the resolution is about 1000 by 1000 pixels. What can be observed on glass sample is that the measured SAE parameter is different inside the channels and on a bounding area between the two channels. Also, inside the channel, the measurement is very repeatable, with a very low standard deviation below 0.1 nanometer. Moreover, on the same sample, we can observe that the results are similar between the two channels, highlighting an homogeneity on a device. However, measurement between two devices show differences, even low. We demonstrated here that AFM could be a very good measurement method for measuring roughness of microfluidic devices. But a limitation has appeared during the project. As the microfluidic devices deal with height of few micrometers, it's not always possible to access to the surface to be measured. A good example is well shown here. The tip can't access to the bottom of the channel as the chip, where it placed the AFM tip, is larger than the channel itself, risking a damaging of the microfluidic device, like it's observed here, or the damaging of the AFM system. Special attention must be taken when designing sample. We want here to thank all the members of the MFMET project teams. And we want to thank you for your attention. You can find more information in the links in the video description and on the project website mfmet.eu. Thanks a lot for watching.